Hi, my name is Benjamin Draves, and I'm a PhD student at Boston University. Today I'm going to be talking about work I've done with my advisor, Daniel Sussman, on bias variance trade-offs in joint spectral embeddings. We're motivated by a data structure entitled multiplex networks. A multiplex network is a collection of networks over a common vertex set, in which the different networks describe a different type of ways the entities can interact. So for an example, this is a multiplex network that describes the Arush Computer Science Department. The vertices correspond to faculty members, postdocs, PhD students, and administrative staff within the department, and each one of the networks describes different ways these individuals can interact. So for instance, if two PhD students have lunch together every day, they will have an edge shared in the lunch network, but if they haven't co-authored a paper together, they will not have an edge shared in the co-author network. So these networks show up in a lot of different settings, such as international trade, transportation system, terrorist group modeling, and neuroscience. And we're going to be focused on ways in which you can analyze these networks. So as an initial attempt to analyze multiplex networks, what one could do is just use methods built for individual network observations and apply them to each one of the networks in the multiplex. So as a toy example here, I have three networks that all exhibit some amount of community structure. And so the red and the blue dots correspond to these community assignments. And I've also plotted their corresponding adjacency matrices beside them. So one method from the individual network analysis literature we could use are something called spectral embeddings. And network embeddings in general are ways in which we can represent networks in a Euclidean space. So we map the vertices of each network to a point in a low-dimensional Euclidean space. And when we can use statistical inference tools from multivariate statistics to answer network-based questions. So for instance, if we want to do community detection here, after we've embedded the networks into Euclidean space, we can just use a clustering algorithm on the points in the right-hand column here to answer this community detection task. So I'll notice here, for the first network, the community detection task seems pretty easy. It seems like a clustering algorithm would be able to recover those community labels well. But for the other two networks, it seemed like this would be very difficult. Alternatively, what we can do is that we can embed the networks in a way that pools together shared information across graphs. So in this way, we can come up with these low-dimensional representations of the networks that in some sense uses the fact that these network objects should be similar in structure. So in the same way as before, we can still apply all of our favorite statistical tools to these embedded points to answer graph problems. So for instance, if we wanted to, again, recover the community labels in this example, we can apply a clustering algorithm to the right-hand side here. But you've noticed by somehow jointly embedding them, the clustering problem becomes easier. The red and the blue points in the right-hand column here are more separated than in the individual network embeddings. So our focus is going to be on trying to understand this joint embedding technique, which is called the omnibus embedding, which I'll talk more about in subsequent slides. To facilitate our analysis of this joint network embedding, we're going to introduce a probability model that'll help us along the way. So we're going to consider we have M graphs over a common vertex set of size n. So M graphs in n vertices. And each vertex, we're going to associate with it a latent position that exists in some low-dimensional Euclidean space of dimension d. We're going to put some restrictions on what these latent positions can be. So first and foremost, we're going to assume they all come from an IID draw from a distribution, which we call an inner product distribution. And an inner product distribution is just a distribution over an appropriate subset of RD, such that for any two vectors in its support, their inner product will fall in the unit interval. Okay? And what we'll do is that with each of these latent positions, we'll put them in the row of a matrix, and we'll call this matrix X. So X is a long and skinny matrix of dimension n by d. Moreover, we're going to associate with each network in the multiplex a diagonal matrix, which I'll call C of G, that along its main diagonal has non-negative entries, and it also has the property that the weighted inner product, so X transpose CGY, falls in the unit interval for all vectors in the support of F. So with this notation, we're now ready to introduce our probability model, which we entitled the eigenscaling random dot product graph. So under this model, we need to make a few more assumptions about the inner product distribution F and the weighting matrices, the CGs, before I can introduce the model fully. So first, if we suppose that if y is drawn from F, and we let delta denote the second moment matrix, we assume that this matrix is diagonal in full rank. Moreover, for these weighting matrices, we assume that it satisfies this min-max assumption. I'll talk a little bit more about these after I introduce the full model and its ramifications on our work. So with these assumptions, we say that a collection of random adjacency matrices, which we denote A, are said to be jointly distributed according to the eigenscaling random dot product graph with latent positions X, if the aijg are conditionally independent with the following form. So the probability of node I and node J sharing an edge in graph G, conditional on their latent positions, is given by this weighted inner product. So in essence, what we're saying is that the edge random variables, the entries of these random adjacency matrices conditional on X, are Bernoulli random variables, and the probability of seeing those edges are given by these inner products. Now, what you should notice here is that the latent positions are fixed across graphs. So the shared structures across graphs in this multiplex will be encoded by these latent positions. We model the heterogeneity between the networks, so the differences in the networks, by these weighting matrices C of G. So coming back to these assumptions, the second assumption, this assumption on the weighting matrices and the assumption that delta is full rank, this is just done to fix the dimension of our latent space to be D. If one of these two assumptions were to not hold, all of the results that we're about to show would go through. It would just be in a lower dimensional space, say D star, which is less than D. Delta being diagonal is a bit more of a restrictive assumption, but it helps us compute analytically some of the things that we'll need in later theorems. So under this model, our goal will be, given our observations of these random adjacency matrices, will be to estimate the products of X times square root of G. So X times square root of G, in some sense, is playing the role of the latent positions for each one of these graphs, scaled appropriately for each. So to estimate these scaled latent positions, these X times square root C's, our first approach might be to totally ignore the fact that these graphs have shared structure and to estimate each one of them individually. So one way we can do that is through an individual embedding technique called the adjacency spectral embedding. And the adjacency spectral embedding was introduced and analyzed by my advisor in his dissertation, and it goes as follows. So if A of G is one of these random adjacency matrices, you take its eigendecomposition and you partition out its eigenvectors and its eigenvalues to correspond to the top D eigenvalues and eigenvectors and the bottom n minus D eigenvectors and eigenvalues. So when I say top eigenvalues here, I mean the most positive. So the embedding, the adjacency spectral embedding, is then defined to be this product UA times SA to the 1/2. So SA to the 1/2, that's a diagonal matrix containing the square root of the most positive D eigenvalues, and UA will have the corresponding eigenvectors in its column. So our estimate for each one of these X times square root of C's will be given by one of these individually. A second approach is to assume that all of the graphs share identical structure and embed the sample mean instead. So instead of individually embedding each one of these networks, what we can do is that we can just create the sample mean matrix by taking the average across all of these adjacency matrices and then looking at its adjacency spectral embedding. A third approach we can employ is to jointly embed the networks, and in essence is to estimate each of these X times square root C's, these scaled latent positions simultaneously. And we'll focus on one such joint embedding, an embedding called the omnibus embedding that was introduced by Keith Levin and a bunch of people at Johns Hopkins in 2017. So the omnibus matrix, which we'll denote as A tilde, is this large block matrix where the main diagonal has each one of these random adjacency matrices and the off diagonal has the average of the ith and the jth random adjacency matrix. And then we say the omnibus embedding of this collection of graphs is given by the ASE of A tilde, and we'll denote that as L hat. So we should note, as A tilde is this large matrix, its dimension is nm by nm, L hat is a matrix that is nm by d dimensional. So each vertex has a different latent position estimate for each one of the graphs. So in essence, what we're doing is we're estimating these scaled latent positions, these X times square roots of C, simultaneously for each one of the graphs. So to compare these three estimators, we set up a small mean squared error simulation in which there are two graphs. The first is drawn from an Erdős-Rényi with parameter p, and p here is equal to a half. And the second graph is an Erdős-Rényi with parameter c squared times p. So under this probability model, the latent positions are all the same. So they're all square root p times 1n. And the scaling matrices here are the identity and c squared times the identity. So if we are thinking about the estimation procedure, in the first graph, we're trying to estimate square root times p, and in the second graph, we're trying to estimate c times square root of p. So we ran this simulation, and we want to compare the mean squared error of the three estimation techniques, and these are the results. So here on the vertical axis is the mean squared error, and on the horizontal axis is the value of c. In red is the A-bar estimator, so this is the embedding of the sample average of the graphs. The green is the individual network embedding that ignores the structure shared across graphs. And the blue is the omnibus embedding, this joint embedding technique. And you can see at c equals 1, the two graphs are identically distributed. So we expect the A-bar method to perform best in terms of MSE. This is the method that assumes that the two graphs have the exact same structure, so it has the lowest mean squared error. But as c starts to go away from 1, the graphs become more and more different. They become more heterogeneous. And the bias that this method induces makes the MSE raise sharply. So for c, for super far values away from 1, you also see that the individual network embeddings seem to be performing the best. So when the networks share very little structure, the individual network embeddings are the best to use. But we see the most robust estimator here is this joint embedding, this omnibus embedding. So the method that in some sense shares the structure between the two graphs has the most robust mean squared error across all three of the methods considered here. So after viewing the results of this simulation, our goal became to establish this bias variance trade-off for these different embedding techniques. So there exist techniques in the literature that allowed us to establish the bias and asymptotic variance of the A-bar and ASE estimators, but no such work had been done on the joint embedding for the omnibus embedding of non-identically distributed graphs. So that became the focus of our work and is the topic of our main results. So before we actually state our main results, just some notation that will show up in the statement of these results. So L hat again is our omnibus embedding estimate. So it comes from the ASC of the omnibus matrix. And we'll let L be this block matrix with S times square root of C's stacked on top of one another. So L hat here, remember, is estimating L. We'll also let I be some integer in 1 to n and G be some integer in 1 to m. And we're going to let H be equal to this combination. So this will pick out the row of L hat that corresponds to the ith node in the Gth graph. And we'll just write that as a column vector so that exists in RD. So with that notation, we're able to state our first main theorem. And this establishes that L hat is a biased estimator for L. So there exists a sequence of diagonal matrices, so these S sub G's, and they're only dependent on C. In fact, it's a one-to-one mapping from these weighting matrices to these S matrices, and a sequence of orthogonal matrices such that when you rotate L hat and you subtract off L, it emits the following decomposition. So the first term here is this SG minus square root of C times XI, and then the second term is just a residual term. So this first term here captures the bias of the omnibus embedding estimate. Remember that we're trying to estimate X times square root of C. And here, this result is saying that L hat is not concentrating around X times square root of C, but is concentrating around these X times S's. Our second main theorem is characterizing this residual, and we do two things. So the first thing is that we put a uniform bound on this residual. So if you look at the maximum Euclidean norm of the rows of R, we show that it decreases to 0 like log n over m. And it has the following asymptotic distribution. So if you scale it by root n, it converges to a mixtures of normals that are centered at 0 and has an explicit but graph-specific variance in terms of these latent positions. So in essence, what this theorem is stating is that L hat is a biased latent position estimator, And we're also able to work out its asymptotic distribution, in addition to putting a uniform rate on the residual term. All of these things put together will help us analyze the bias variance trade-off in subsequent analysis, as well as some of the statistical applications that utilize the rows of L-hat. So having established this bias variance trade-off, we now turn to analyzing its effect in statistical applications that utilize these omnibus embedding techniques. So we consider two applications, both community detection and network hypothesis testing, and we do so in the following simulation experiment. So the first thing we'll do is that we'll draw x1 through xn, so the latent positions from an inner product distribution, where that inner product distribution corresponds to a two-group stochastic block model with within group probability of 0.25 and between group probability is 0.05. And then what we'll do is that for some value of t, we will draw the random adjacency matrices from an eigenscaled random dot product graph with C's being given as follows. So C1 will be the identity. So regardless of the value of t, the first graph will correspond to this stochastic block model. And C2 will be given by this diagonal matrix. So 1 plus t and 1 minus t respectively on its main diagonal. And then what we'll do is that with those random adjacency matrices, we'll jointly embed them to get our omnibus embedding estimate L hat. So we set up C2, this matrix that depends on t, in such a way that at t equals 0, A2 is also a stochastic block model, so it's IID with the first network, but at t equals 1, A2 is an Erdős-Rényi graph with parameter p equals 0.3. So you can think of C2 as starting as a strong stochastic block model, a very clear stochastic block model that slowly starts to integrate itself into an Erdős-Rényi. So the community structure that exhibits slowly dwindles away. So the goal again is to analyze techniques that utilize L hat for statistical inference. So under this simulation experiment, one task that we can consider is to recover the community labels corresponding to the inner product distribution. So recovering the community labels corresponding to the stochastic block model using the rows of L hat. So one way in which we can do this is to apply a clustering technique to this X bar, which we call omnibar in our preprint matrix. So all we're going to do is if we take the first n by d block of L hat, we're just going to average it with the second n by d block of L hat. So this is essentially as you're averaging the two latent position estimates corresponding to graph 1 and graph 2. And so when you apply Gaussian mixture models to this, these are the results of that simulation in comparison to other community detection algorithms. So here on the vertical axis is the misclassification rate, and on the horizontal axis is t. So remember, as t gets larger, the networks become more heterogeneous and the clustering problem becomes more difficult. So in the purple here and this blue are methods that correspond to individual embeddings, and this red line right here corresponds to this Gaussian mixture models applied to X bar. So the other three methods on the screen are other joint embedding techniques. And so you can see that for at least small values of t, each one of these joint embedding techniques has smaller misclassification rates than either of the individual embeddings. And you can see that the omnibar method seems to be outperforming those as well. We also look at different examples where this omnibar method does better than some of the optimal joint embedding techniques here too. So I think a takeaway from this slide should be that the bias doesn't ultimately hurt you in this case. So even if we're getting biased latent position estimates, it doesn't seem to affect the performance of classification algorithms applied to the rows of this omnibar matrix. Second statistical application that we consider is the two-graph hypothesis testing problem. And in particular, we want to test the hypothesis that the two networks share the same weighting matrix, or C1 is equal to C2. So by characterizing the asymptotic joint distribution of the rows of the omnibus embedding, we're able to construct a pivotal test statistic that's based on the Mahalanobis distance between the rows of X hat 1 and X hat 2. So within the context of our simulation experiment, we wanted to compare the empirical power of this test statistic with existing test statistics. So here on the vertical axis is the empirical power, and on the y-axis is different values of t. So remember again, t at 0 is when we are in the null, so C1 is equal to C2, and as t goes away from 0, we are in the alternative, C1 does not equal C2. The red line here corresponds to a test statistic that was used in the original omnibus paper that's based on the Euclidean distance between x1 hat and x2 hat. And the blue, purple, and green curves here correspond to test statistics that are based off of our pivotal test statistic. And you'll notice for networks of size 200, all three of these methods appear to be higher power than this Euclidean-based statistic. Now, there are still some issues with this statistic. So this purple statistic is the one that we've proposed using in practice because it's totally estimable from the data. So even for moderate network sizes, it doesn't achieve level. And we're working on some finite corrections for this. But it shows that by characterizing the asymptotic distribution of these estimates, we're able to construct test statistics that more accurately reflect changes in the underlying model parameters. So in conclusion, we're able to establish a bias variance trade-off for the estimation of latent positions produced by the omnibus embedding in the presence of heterogeneous network data. This bias variance trade-off also speaks to the robustness of the omnibus embedding and shows that joint embedding techniques that are effective at pooling information that is shared across networks can be the most robust estimator for these latent positions. Not only that, we showed that this bias variance trade-off can help in downstream statistical tasks, such as community detection and network hypothesis testing. So we spell out all of these details in our preprint, which is available on arXiv now. And currently we're working on some future directions of this work that including extending the analysis beyond the eigenscaling random dot product graph to encapsulate more general graph models. We'd also like to get a power analysis for our proposed test statistic and refine finite sample testing procedures to fix some of the level problems that we were seeing on those power curves. So I thank you for tuning in, or at least clicking on the link, and I hope you have a good day.